Thank you, Professor Hartwig. It is an honor to listen to you. And we have many questions from the audience. Let's start the Q&A session. Starting with a very interesting question. It is that if you could start your research program over again, knowing what you know now, where would you focus your efforts? Would you be still continuing the homogeneous CS activation or heterogeneous or cross-coupling chemistry? Or is there another area that you would delve into?
That's a tough question. I guess is the question if I knew what I knew now and I was starting today, or if I was starting back when I started? Do you know? I guess I could answer both, right? I mean, there's many problems to work on today, and I think our group has evolved in what we worked on. We did a lot of organometallic chemistry early to reveal fundamentals, and we continue to do that. But now try to work into more practical transformations and studying the mechanisms of those. But we've evolved to working on biocatalysis and what we were calling chemoenzymatic catalysis to take chemical principles to that. I think that's a really viable area. I think the polymer upcycling is. Of course, there's lots of methods being developed through, first row metals and radicals and light and electrochemistry, as well as, what we're calling thermal chemistry. I wouldn't say that, one is the right thing to do over the other. People have to find the openings and view their own creativity. I remember what a colleague once mentioned way back early in my career when we were doing a faculty search, and I asked him, so what person do we want to hire? What do you think the future is? And he said, well, that's what we're going to learn when we interview these people, because they're the ones who are going to have the ideas for what is in the future. So yeah, we hope that young people who we hire are going to have define what the future is. We don't want to define it. We want what people decide to do to define it. So sorry, that's a cop out of an answer, but I don't want to say that I would. I think what we chose to do was has been pretty rewarding to us.
Yeah. Thank you. That's a very insightful response from your side. So moving to the next question, between homogeneous and heterogeneous catalysis pathway, which one gives better crystallinity?
Let's see. I guess I'm looking. Are these questions on which gives better crystallinity?
Crystallinity, yes.
Oh, well, I guess I'm not sure what the question's asking. I mean, the catalysts themselves, right, are of course very different form, but the product that we make, they're all liquids and gases. So, yeah, maybe if there was a clarification of the question, I could answer that.
Okay, yeah, thank you. Moving to the next question. Is it possible to functionalize selectively a specific carbon in the same and also even cleave molecules that needs further functionalizations?
Yeah, I don't know any way to cleave specifically in the chain. You could imagine clipping off at the first carbon being different, carbon-carbon bond being different than the others, but we don't actually want to make methane. So we're actually trying to avoid cleaving that carbon. You can imagine some size selectivity, but that's a grand challenge. I mean, I guess you could call it that. I mean, nobody has a really good way to directly, clip off 8 carbons to make octene that is a valuable monomer for polymerization. So far, nobody's been able to do that.
Okay, thank you. The next question, are there any particular side reactions that could be potential concern when recovering propene?
Let's see. So, one of the valuable features of our reaction is the lack of formation of alkane, very, very small amounts of alkane. The really difficult separation, I'm told, is to separate alkenes from alkanes. So if we made propane and propene, that would be very difficult to separate. And I showed early on that some of our early results was making that mixture that we tried to avoid. So that's a major issue. The other major issue, is we're using ethylene and we have excess ethylene. So we need to separate the ethylene from the propene. So it's not so much formation of side products, But that separation is done commercially. It's well known, established how to do that. But it's a cryogenic one, and it takes some energy to separate the propane and the ethylene and the propene, and then get that back. But one of the side reactions that people see that we avoid is the formation of alkane.
Got you. Thank you. The next question: why is the molecular weight of P reduced a lot after dehydrogenation? And he believes that it is just the removal of hydrogens in the P backbone. So why is the molecular weight of the P reduced?
So the molecular weight in the heterogeneous catalysis I showed, right, at 320, the molecular weight is reduced just by thermal cracking, we think, because the molecular weight doesn't change that much with the added catalyst. It's a bit more with the sodium catalyst than the tungsten. And that's just a thermal cracking. Like that's, what people, are concerned about with recycling, right? You take the polyolefin, you put it in an extruder, and at high temperature, and you crack the chains. Now, CC bonds aren't just like ethane doesn't just crack its CC bond at 320 degrees. The bond's too strong. So that's partly due to mechanical process. It's like a sort of mechanochemistry kind of process that's well established and not that well understood as far as I know, if looking at the literature.
Okay. Thank you. The next question: what is the driving force for the selectivity for the primary versus secondary CH borylation reaction?
Yeah, that's a good question. And we have looked at that and published on that a couple times. The simple answer is it's a steric effect, but it's actually a bit more complex than that. Early days, we showed that the primary CH bond is cleaved in preference over secondary CH bond with a ratio, I think, of about 7-1. And that's, the selectivity for the borylation process overall was much higher. So it's actually the formation of the boron carbon bond. The reductive elimination has a much higher barrier when you're coupling the secondary than the primary alkyl. So if you're reversibly cleaving the CH bonds, it's going to preferentially couple at the primary over secondary for steric effects there. But also, it's pretty well established that the primary alkyl is more stable than a secondary alkyl when you don't have polar groups on the material. And you can think about that again for sterics, but also electronic effects, right? If you have partial negative charge on the carbon that's bound to the metal, that partial negative charge is more stable on a primary than secondary carbon. So all of those lead to the selectivity we observe. But, that's kind of unique to organometallic chemistry, but it is a rare process that actually is catalytic and gives this high selectivity without directing groups.
Yeah, thank you. Moving to the next question. Could you also comment on the life cycle analysis of the polyolefin upcycling?
We're working on that, actually. It is so relative to making virgin material in some published literature on the overall process. It is has a smaller CO2 footprint. We haven't delved into it in enough detail with the heterogeneous system and how we're doing it to be able to give a specific number, but it may be like around 20% less. And part of that is because we're using ethylene to make the propene. If we make products that have more longer chain lengths, then more of the carbon is coming from the polyolefin, less from the ethylene. And so then the economics work better and the life cycle analysis is better. So we're thinking of really focusing, in addition to propene, focusing on the long chain alkenes for that reason.
Thank you. We have so many questions, but for the interest of time, we'll be taking one final question. Could you please share your motivation to work on polyolefin upcycling?
Yeah, I guess the motivation is is environmental, right? It's a complicated issue, right, as to how much of it is You know, is a chemical problem, how much of it is a waste management problem, how much of it is human behavior problem. But there's no question that, you know, even if we make new materials that are going to have greater circularity, you know, we make so much polyolefin, right? If there is a way to take that material and turn it into something useful, give it an extra life, whether it's one life or multiple life cycles, that there could be a benefit because it's, you know, hundreds of billions of pounds worth of material per year. So, you know, that's been the practical motivation. On the scientific side, I guess I didn't really mention this, but, you know, polyesters can be taken apart because you have these ester bonds that you can just do, you know, methanolysis or hydrolysis of. So we know that we can take polyethylene terephthalate and bring it back to monomer. And so the scientific challenge, right, is how are you going to cleave the carbon-carbon bonds in a selective way to get back to, you know, one material from polyolefins? And so on the scientific side, I think what we've been really excited about is that we showed that you can deconstruct a polyolefin the way that you deconstruct polyesters. Now, I was at a Eastman plant in Tennessee recently where they have a plant now to do the deconstruction of polyesters on a commercial scale. So we're really far away from doing that with polyolefins, but at least we showed that the chemistry can be done in a similar way, catalytically, to get to back to monomer. Yeah.
Okay. Thank you, Professor Hartwig. It's been a really engaging and interesting Q&A session. With this, we end this Q&A session and